Welcome, good afternoon. Today we are going to be continuing our group 15 class. So yes, in the last class we had done till dinitrogen, that is an important compound of nitrogen. So nitrogen is present as dinitrogen in the atmosphere. Today we will be continuing, and this is ammonia now. So a very important hydride of nitrogen is ammonia. NH3. So if you talk about the structure of ammonia, in ammonia nitrogen is sp3 hybridized. So the geometry is tetrahedral with one position occupied by a lone pair, alright, and the shape would be pyramidal. If we talk about the preparation of ammonia, the first method is from decay of nitrogenous organic matter. So ammonia is present in little amount in the air as well as soil, and that is found because of decay of nitrogenous organic matter in the soil. So this is urea, NH2CO NH2. Urea on decay with water gives us ammonium carbonate first, NH4 whole twice CO3. This is ammonium carbonate, which further gives us the final decay products, which are ammonia, water and carbon dioxide. So this is the first method by which ammonia is prepared biologically in the atmosphere. Now on a small scale in the lab, you can prepare ammonia by treating ammonium salt. So you see NH4Cl, NH4 whole twice SO4. So ammonium chloride and ammonium sulfate. These are salts of ammonia. Good afternoon. These are salts of ammonia which are formed with strong acids. So NH4Cl is formed by a strong acid HCl, and NH4 whole twice SO4 is formed by a strong acid H2SO4. So ammonia forms salts with strong acids because ammonia is weakly basic. Now when you decompose these salts with calcium hydroxide or caustic soda, that is NaOH, we get ammonia, water, and in this particular case we get calcium chloride, and with ammonium sulfate we get sodium sulfate. Okay, so this is the lab method of preparation of ammonia. So you take ammonium salts and you decompose them with calcium hydroxide and caustic soda. Now the third process, which is very important, is for the industrial manufacture of ammonia, and that is called the Haber-Bosch process. So look at this reaction here, and then I'll explain how this process really works. So the reaction for the preparation of ammonia on a commercial scale is directly mixing nitrogen and hydrogen in the ratio 1:3, 1 mole of nitrogen with 3 moles of hydrogen, giving us 2 moles of ammonia. Alright, this is a reversible reaction and it is exothermic. So delta H formation is minus 46.1. Now let us see what exactly is happening in this Haber's process. So Fritz Haber was the scientist who found out that using this particular reaction we can directly combine nitrogen and hydrogen to give ammonia. He was awarded the Nobel Prize for this. There was another chemical engineer called Carl Bosch who used this reaction and upscaled it so that it suited the needs of the industry. So he developed the entire plant in which ammonia could be produced industrially on a large scale. So that's why this is called the Haber-Bosch process. Now if we go back to that reaction, it's a reversible reaction, so Lee-Chatter's principle would apply here. You see the number of moles of gases that are present in the reactant. So 3 plus 1, 4 moles, and in the product we have 2 moles of the gas. So this means a condition of high pressure. If we are increasing the pressure for this particular reaction, to negate that effect, this reaction would move in the forward direction. So high pressure is one important condition, and since it's an exothermic reaction, low temperature. So high pressure and low temperature are required. But at a low temperature, the rate of attainment of equilibrium is very slow. So that is not feasible economically, that's not a viable way. So in the actual process, we don't use a very low temperature. And another thing, since the reaction is so slow, we would need a catalyst to produce it industrially. So the ideal conditions in the industry are a pressure of about 200 atmosphere here, a temperature of around 700 Kelvin, and the use of promoted iron as the catalyst. So the catalyst that is used is iron oxide Fe2O3 with small amounts of K2O and Al2O3. So these are the conditions that in actuality in the industrial plant for production of ammonia are used. So what happens when you feed nitrogen and hydrogen in the plant? So these are the two gases, they are put through a compressor to compress the gases and get the pressure of around 200 atmosphere. These are now fed into a chamber where the catalyst is present. Alright, the catalyst of iron oxide with K2 and Al2O3 is present here. So these two gases are compressed and then fed into this chamber. Out of this chamber comes ammonia, and over one cycle, one pass of these two gases over the catalyst gives a 15% conversion. So only 15% of these gases get converted to ammonia. So here that 15% of gases which are ammonia now are condensed, cooled and condensed, so we get liquid ammonia here. Remaining nitrogen and hydrogen are recycled. So N2 and H2, we have liquid ammonia here, N2 and H2 are recycled here. So we have a pump which pulls up these gases from here and then feeds them again in this chamber where the catalyst is. And obviously these gases are again compressed to a pressure of about 200 atmosphere. So this is the entire process, the Haber-Bosch process by which ammonia is produced industrially, and this is very important. The conditions required are also important even from your Neet point of view. So this is it about the Haber-Bosch process. Moving on. So ammonia is a colorless gas. It has a very pungent smell. The odor is really bad. It hits your nose. It is so bad. And it is slightly toxic also. We have already spoken about the structure of ammonia. So one position is occupied by a lone pair. This bond angle NH is 101.7 picometer. And the bond angle is 107.8. So you see this bond angle, we have already discussed about it. This bond angle is less than the regular tetrahedral angle, and that is because of the repulsion between this lone pair and the bond pairs, right? Now, the higher melting and boiling points than expected on the basis of molecular mass. How do you explain that ammonia has a higher melting and boiling point? Because the molecular mass, if you see all the group 15 elements and their hydrides, the molecular mass is increasing on going down the group. But the boiling point and melting point of ammonia are higher than they should be. The reason for that is hydrogen bonding. So, in ammonia, nitrogen is attached to hydrogen. Since nitrogen is an electronegative element, ammonia molecules are hydrogen bonded, like this. So, we have another ammonia molecule. So because of this hydrogen bonding, what happens, all the molecules of ammonia are associated more strongly together. They are not just discrete molecules held by weak van der Waals forces. There are discrete molecules, but they are held together by hydrogen bonds. For you to understand how important hydrogen bonding is, it's a weak force. But to realize the importance of this hydrogen bonding, you see water. So water is a liquid only because there is hydrogen bonding present. Otherwise, if you go down in group 16, after oxygen you have sulfur, so H2S is a gas, but water is a liquid. So all life as we know it on this planet exists only because water is a liquid. And water is a liquid, why? It is not a gas, it is a liquid, why? Because of hydrogen bonding. So hydrogen bonding is extremely important. Even though they are weak forces, it is important that hydrogen bonding is taking place and it is having a lot of repercussions on the properties of the molecule. So in the case of ammonia, it has higher melting and boiling points than expected. Now, ammonia has a lone pair of electrons on it, alright. An aqueous solution of ammonia is weakly basic. Why is it basic? Because ammonia takes up H plus from water. Why does it take up H plus? Because of this lone pair. So we have ammonia with a lone pair of nitrogen and we have water. This lone pair can form a bond with proton, alright. So it takes up H plus from water and furnishes OH minus ions. So obviously this is a reversible reaction. It only partially dissociates in water to give us OH minus. That is why a solution of ammonia is weakly basic. Now, because ammonia is basic in nature, it precipitates the hydroxides of many metals from their salts. So look at this reaction here. ZnSO4 zinc sulfate reacting with ammonium hydroxide. This is a salt of a weak base. Reacting with ZnSO4, it forms a stronger base, ZnOH whole twice, and precipitates it. This is a solid and we get ammonium sulfate. Also, we have FeCl3 reacting with ammonium hydroxide. So it gives the hydrated oxide of iron, Fe2O3.X H2O solid plus ammonium chloride aqueous. So this is a brown precipitate. So because ammonia is weakly basic, it precipitates the hydroxides of many metals from their salt solutions. Alright, so we have already discussed that it is basic. It is basic and it can be categorized as a Lewis base also. How is it a Lewis base? Because it can give or donate the electron pair and form a linkage with metal ions. So now this interesting property of ammonia, because of which it can donate its electron pair and form linkages with metal ions, helps in detection of metal ions like copper and silver. So Cu2 plus and Ag plus. So if we have a solution containing Cu2 plus or Ag plus, how do you detect that using ammonia? So we'll see a solution of copper 2 plus, like copper sulfate for example, is bluish in color. Okay, this is blue in color. If you pass ammonia through it, what will happen? It will form a complex with Cu2 plus. So the complex is CuNH3 whole 4. So 4 molecules of ammonia will associate themselves around copper and we will get a complex which is deep blue in color. So from blue, the complex goes to deep blue, and that is how you detect that a given solution had Cu2 plus. So detection of Cu2 plus is done this way. Now see what happens in the case of Ag plus. So we have Ag plus. When it reacts with ammonia, it gives us AgNH3 forming a complex with 2 molecules of ammonia plus. Alright. The problem here is that this is colorless and this is also colorless. So how do you detect? In this case, in the case of copper, what was happening? From blue you were getting a deep blue color. So you could see that some change is happening. But if the solution stays colorless, how do you know that ammonia has formed a complex with the metal ion and that metal ion is silver? So for that, you first precipitate this Ag plus, which might be present as, let's say, silver nitrate. So you have a silver nitrate solution. So you precipitate it with Cl minus. So Ag plus with Cl minus gives a white precipitate of AgCl. This is white in color. Now when you make AgCl react with ammonia, now a complex has been formed between Ag plus and ammonia, giving us a colorless solution again. So what is the sequence of color change? From colorless you get white and then you again get colorless. So this is how you get to know that Ag plus ions were present. So because it is a Lewis base, ammonia can be used for the detection of metal ions like copper 2 plus and Ag plus. So another interesting thing about ammonia forms salts, right? So NH4Cl is a salt we spoke about. So it is the formation of this salt is a method of detecting the presence of ammonia. One is its pungent smell, otherwise if you are doing a reaction in which, let's say, ammonia is released and you need to detect the presence of ammonia, what do? Near the test tube or near the source where ammonia is getting produced, supposedly, you bring a stopper. So there are glass bottles in the lab, right? If there is a bottle of HCl, conc HCl, you bring the stopper which contains some drops of HCl on it near the source where ammonia is getting released. So you will get white fumes. So that is because ammonia reacts with HCl to give white fumes of NH4Cl. So this is an interesting reaction where you see that ammonia is forming a salt with an acid, and you can detect the presence of ammonia because of that. So white fumes of NH4Cl. Alright, moving on. So now we have to talk about the oxides of nitrogen. This is very interesting. The first oxide of nitrogen forms numerous oxides, okay, and the oxides of nitrogen are different from those of phosphorus. What is the difference between nitrogen and phosphorus? Nitrogen can form p-pi bonds, whereas phosphorus cannot form p-pi bonds. So if you see this particular oxide here, we know they form oxides of type E2O3 and E2O5. In the case of phosphorus, these P2O3 and P2O5, something wrong with the pen, E2O3 and E2O5, they always exist as dimers because phosphorus cannot form p-pi bonds. Phosphorus can form d-pi bonds with oxygen, but not p-pi bonds. Alright, now moving on. So nitrogen forms a variety of oxides. It's small in size, high electronegativity, and it can form p-pi multiple bonds. So the first oxide of nitrogen is N2O, which is also called nitrous acid. You need to know the names because sometimes in the paper, nitrogen 1 oxide will not be written, clearly telling you that nitrogen is present in the +1 oxidation state. No, sometimes nitrous oxide can also be there, so you need to remember the different names of the acids, okay. So in nitrous oxide, what happens, it's N2O. The oxidation state of nitrogen is +1. So the oxides of nitrogen are formed from +1, 2, 3, 4, 5. So all oxidation states, positive oxidation states, are observed in oxides of nitrogen. Now, why are these states positive? A positive क्यों है states? Because nitrogen is bonded to oxygen. Oxygen is more electronegative. That means it will keep the shared pair of electrons towards itself. Hence, a positive oxygen state on nitrogen and a negative oxygen state on oxygen. So, talking about the first one, N2O, it is formed. Now, methods of preparation are also important. So, you need to look here. So, it is formed by thermal decomposition of ammonium nitrate. NH4NO3 on heating gives us N2O and H2O. So, it is formed by thermal decomposition of ammonium nitrate. This oxide is colorless and it is neutral. So, the first two oxides of nitrogen, so you know nitrogen is a non-metal. Non-metal oxides are acidic in nature. But the first two oxides here in the lower oxidation states, +1 and +2, both are neutral. The rest of the oxides are acidic. And how do you see if the acidity is increasing or decreasing? So for the rest of the oxides, the oxidation number is +3, +4 and +5. So with the increase in oxidation number, the acidity of the oxide also increases. So going down here from N2O3 to N2O5, we can say that the acidity increases. Coming back, so this is a colorless gas and it is neutral. So this is the first oxide, nitrous oxide. There are two interesting things about nitrous oxide. So nitrous oxide is tasteless and it is non-toxic. So it is used as a propellant for whipped ice cream. So when you have ice cream in those cones which is whipped and little fluffy and frothy, that is because of N2O. And N2O in small amounts also causes euphoria. That is why N2O is also called the laughing gas. Right? So this was nitrous oxide. The second oxide of nitrogen is NO, which is also called nitric oxide. The oxidation state of nitrogen in NO is +2. This is also a neutral oxide and it is also a colorless gas. Now NO is produced when NaNO2, sodium nitrite, reacts with FeSO4 and H2SO4, right? NaNO2, FeSO4 and H2SO4. So we get ferric sulfate, Fe2 plus gets oxidized to Fe3 plus. We get sodium hydrogen sulfate, and NO2 minus here is becoming NO here. So we get NO. Okay, so iron is getting oxidized and nitrogen is getting reduced. So we get the formation of NO, that is nitric oxide. One very interesting thing about nitric oxide, so if you count the number of valence electrons of NO, 5 valence electrons from nitrogen, 6 valence electrons from oxygen. This gives us 11 electrons in the outermost shell. This means it is an odd electron molecule. An odd electron molecule is paramagnetic. So it has an unpaired electron. So nitrogen monoxide or nitric acid has a tendency to dimerize in the solid and liquid form. Got it? So you add the total number of valence electrons. If it is an odd number, that means it's an odd electron molecule and it is paramagnetic. So its tendency is not that high, but it does have a tendency to dimerize, form a dimer in liquid and solid forms. There's another interesting thing about nitric oxide. So NO has an ability to form complexes with metal ions. So NO forms complexes with metal ions. So this ability of NO to form complexes with metal ions is used in the brown ring test, which we will just study under nitric acid. So brown ring test, where NO forms a complex with Fe2 plus. Okay. Next is dinitrogen trioxide. So N2O3. There is no other name for it. It is dinitrogen trioxide. Here the oxidation state of nitrogen is +3, right? It is formed by condensing an equimolar mixture of NO and NO2. An equimolar mixture of NO and NO2 on condensing at a low temperature. So it can be prepared only at a low temperature of 250 Kelvin. Equimolar mixture of NO and NO2 gives us N2O3. Now this oxide is acidic in nature. Alright, from +3 onwards, +3 oxidation state, the oxides are acidic in nature and it is a blue solid. So to remember the color is also sometimes important, because you can get a question where they can say an equimolar mixture of NO and NO2 gives a blue colored solid. So they might not directly tell you that an oxide of nitrogen is getting formed, but it's just a blue colored solid. So you'll have to recollect. So here in all of these, only 2 are colored. One is N2O3 and the other one is NO2, which is a brown gas. Okay. Now N2O3 is an anhydride of HNO2. Anhydride of nitrous acid, HNO2. So what does that mean? So when N2O3 reacts with water, it gives us HNO2. So N2O3 is an anhydride of HNO2. The next oxide is nitrogen dioxide, NO2. Nitrogen dioxide has nitrogen in the +4 state. This is a brown gas, this is toxic, and it is also acidic. So again, if we count the valence electrons of NO2, so 5 electrons from nitrogen, 6 plus 6, 12 electrons from oxygens gives us 17 electrons. So what is happening here? It is an odd electron molecule. Odd electron molecule. It is paramagnetic. So it also has a tendency to dimerize, and it gives a dimer which is N2O4, which is the next oxide. We'll just come to that. Now, if we come to the preparation of NO2, it is formed by heating lead nitrate, PbNO3 whole twice, upon heating to 673 Kelvin gives us NO2 plus PbO plus O2. So this is how you get this gas. Alright, now this gas is a brown liquid. It's a gas, brown gas. You cool it down, it becomes a brown liquid. On further cooling, it keeps on getting paler and eventually it becomes a colorless solid. So what is that colorless solid? Here NO2 is paramagnetic. So on cooling, it gives us the dimer N2O. So this dimer N2O is colorless. It is colorless, it is diamagnetic. Alright, so when you're cooling the brown liquid, you're eventually getting a colorless solid, which is N2O. N2O is dinitrogen tetroxide, which is the next oxide of nitrogen. So that is N2O4. In N2O4, nitrogen is in a +4 oxidation state again. Now you look here, this is the exact reaction which I wrote here. So on cooling, NO2 gives us N2O4, and if N2O4 is heated, it gives us back nitrogen dioxide. So it is a strong temperature dependent equilibrium. So at a temperature of around 100 degrees, what would it mean? That means you're heating it around 100 degrees, 90% of the vapors will be NO2, only 10% will be N2O4. So this is strongly temperature dependent. It is a colorless solid, which we have already discussed, colorless solid, colorless liquid, and it is acidic in nature. So all the oxides from this onwards, I need help from the technical team. Can you please switch the screen back? Okay, thank you so much. So where were we? Yeah. So it is acidic. So all the oxides from N2O3 onwards are acidic. Now coming to the last oxide, that is dinitrogen pentoxide, N2O5. N2O5 has nitrogen in the +5 oxidation state. Okay, so oxidation state is the number of electrons an atom is either gaining or sharing to form a bond. So here nitrogen is using all 5 of its electrons, valence electrons, and the oxidation state is +5. How is dinitrogen pentoxide prepared? So it is interesting to look at this reaction here. It is prepared by careful dehydration of HNO3 using P4O10. Okay, so there are two things that are hidden in the statement I just said. HNO3 को dehydrate करा है with P4O10. This gives us HPO3 and N2O5. Okay, so we are getting dinitrogen pentoxide. So what does it tell us about HNO3 and P4O10 here? It tells us that N2O5 is an anhydride of nitric acid. So N2O5 is an anhydride of nitric acid. इसका क्या मतलब हुआ? If N2O5 is dissolved in water, it gives us HNO3. So N2O5 is an anhydride of nitric acid. दूसरी चीज़ हमें इससे क्या पता चल रही है? Let's talk about P4O10. P4O10 is a phosphorus oxide. P4O10 is a dehydrating agent. इससे हमें पता चल गया. अब you remember we spoke about the two types of oxide of phosphorus and nitrogen. So phosphorus के oxides are always present as dimers. So this P4O10 is in actuality P2O5. So sometimes in your paper P2O5 भी लिखा आता है. So when you see P2O5, that actually means P4O10. और अगर P2O5 लिखा है या P4O10 लिखा है तो वो dehydrating agent है. ठीक है? So इस reaction से ये दो तीन बातें पता चलती हैं हमें. One, N2O5 is an anhydride of HNO3. और दूसरा P4O10 is the dimer of P2O5. P2O5 exists as a dimer and it is a dehydrating agent. Again, this is a colorless solid and this is acidic. One more thing about N2O4. So dinitrogen tetroxide, the one which is a dimer of NO2 on dissolving in water. So we have N2O4, water में dissolve करने से this one gives a mixture of HNO2 and HNO3. ठीक है, so N2O3 water में HNO2 देता है, dinitrogen trioxide is giving us nitrous acid, N2O4 is giving us a mixture of nitrous acid and nitric acid, and N2O5 gives us HNO3 nitric acid. ठीक है, तो ये तीन एसिड्स का किस चीज़ का एनहाइड्राइड है ये इन रिएक्शन से पता चलता है. ओके, मूविंग ऑन. चलो, द स्ट्रक्चर्स ऑफ ऑक्साइड्स ऑफ नाइट्रोजन. N2O का स्ट्रक्चर इज लीनियर. ठीक है, सो ये लोएस्ट डॉट स्ट्रक्चर्स है, उनके रेजोनेंस स्ट्रक्चर है. तो यू काउंट द टोटल नंबर ऑफ वैलेंस इलेक्ट्रॉन्स एंड उनको डिस्ट्रीब्यूट करो, तो इसमें 8 इलेक्ट्रॉन्स इस वाले स्ट्रक्चर में बॉन्ड फॉर्म करे हुए हैं और बाकी के 8 कहाँ पे यूज हुए हैं एज लोन पेयर्स. सो दीज आर द टू रेजोनेटिंग स्ट्रक्चर्स. इट इज अ लीनियर फॉर्म. ठीक है, NO नाइट्रिक ऑक्साइड का ये स्ट्रक्चर है. सो इसमें एक इलेक्ट्रॉन जो अनपेयर्ड था इस वाले स्ट्रक्चर में यहाँ पे है और इस वाले स्ट्रक्चर में यहाँ पे है. इफ यू टॉक अबाउट N2O3, इट हैज़ अ प्लेनर स्ट्रक्चर. ठीक है, प्लेनर स्ट्रक्चर, and you distribute the valence electrons under these two resonating structures. When it comes to NO2, this is the structure of NO2. जो unpaired electron है NO2 में, it stays on nitrogen, दोनों स्ट्रक्चर में. ठीक है, ये रहा वो unpaired electron. अब इसमें एक और इंटरेस्टिंग चीज़ देखने की है कि इसका बॉन्ड एंगल क्या है, 134. सो ये नाइट्रोजन यहाँ पे sp2 हाइब्रिडाइज्ड है इन NO2. सो आइडियल बॉन्ड एंगल sp2 हाइब्रिडाइजेशन के लिए क्या होता है, प्लेनर ट्राइंगल होता है तो 120 होता है. इस केस में क्या है, इट इज़ 134. इट इज़ मोर देन 120. वाई? बिकॉज जो ये एक ऑर्बिटल सिंगल इलेक्ट्रॉन ने ऑक्यूपाई किया है, द रिपल्शन बिटवीन द सिंगल इलेक्ट्रॉन एंड द बॉन्ड पेयर इज लेस कंपेयर टू रिपल्शन बिटवीन लोन पेयर एंड बॉन्ड पेयर. ठीक है, दैट मीन्स ये जो NO बॉन्ड्स हैं दे कैन स्प्रेड आउट, क्योंकि ऊपर से जो सिंगल इलेक्ट्रॉन है उसकी रिपल्शन नहीं है. ठीक है, दैट इज वाई इट इज 134. N2O4 इसका डाइमर है. सो ये अनपेयर्ड इलेक्ट्रॉन यहाँ पे पेयर हो गया. सो अगेन यू गेट अ प्लेनर स्ट्रक्चर. एंड N2O5 का स्ट्रक्चर प्लेनर है, वो ये वाला स्ट्रक्चर है. ठीक है, ओके. नाउ द इम्पॉर्टेंट ऑक्सो एसिड ऑफ नाइट्रोजन. ऑक्सो एसिड्स आर एसिड्स जिनमें हाइड्रोजन एंड ऑक्सीजन दोनों होती हैं और वो एसिड्स होते हैं. नाइट्रोजन के बहुत सारे ऑक्सो एसिड्स हैं, लाइक H2N2O2 हाइपोनाइट्रस एसिड, देन HNO2 नाइट्रस एसिड and HNO3 nitric acid. So if you talk about the production of acids in tonnage, HCl, H2SO4 and HNO3, three most important acids which are produced in the maximum amount in the world. Nitric acid is one of them. So in your book we just have nitric acid to be discussed in detail. We'll be talking about it now. Right, if you see the preparation of nitric acid, the first method is by heating KNO3 or NaNO3, potassium nitrate or sodium nitrate with H2SO4. So what happens when we have sodium nitrate reacting with H2SO4? You get the production of HNO3 here. NaHSO4, sodium hydrogen sulfate and HNO3. Remember this reaction because this takes place in the brown ring test also. We will discuss it in 2 minutes now. Okay. So this is the first method of preparation in the lab. Now on a large scale, it is prepared by Ostwald's methods. So Ostwald's method is based on the oxidation, catalytic oxidation of ammonia from atmospheric oxygen. So ammonia को oxidize कर रहे हैं from अमोनिया को ऑक्सीडाइज करा फ्रॉम ऑक्सीजन फ्रॉम द एयर यूजिंग अ कैटलिस्ट. सो फर्स्ट स्टेप इन ऑस्वाल्ड्स प्रोसेस, आई विल मार्क इट एज ए, इज अमोनिया गेटिंग ऑक्सीडाइज्ड. सो जब अमोनिया का ऑक्सीडेशन फ्रॉम एयर करते हैं, you see which catalysts are getting used, because to remember such things are important. So it's a platinum rhodium gauge catalyst. The temperature is 500 Kelvin and the pressure is 9 bar. So under these conditions you get NO and H2. In the first step of Ostwald's process, ammonia reacts with oxygen giving us NO. Second step mein NO gets oxidized. So in the second step B, nitric oxide combines with oxygen to give NO2. So this is the second reaction. NO plus O2 gives NO2. All right. Third step में क्या होता है? Marking it as C. जो NO2 form हुआ है, it dissolves in water to give HNO3. So third step में HNO3 form होता है. So third step का क्या reaction है? Nitrogen dioxide NO2 dissolves in water to give us HNO3 plus NO. अब ये रिएक्शन आपकी बुक में लिखा हुआ है. ओके. सो अभी थोड़ी देर पहले हमने बात की थी कि NO2 वाटर में डिजॉल्व करके HNO3 एंड NO देता है. सो जो NO बन रहा है, NO क्या होता है, ये NO को हम रिसाइकिल कर लेते हैं इस वाले स्टेप में. ठीक है. सो NO यहाँ पे रिसाइकिल हो जाता है और ये वापस ऑक्सीजन से कम्बाइन करके NO2 दे देता है. ऑल राइट. राइट. एंड व्हाट एल्स? सो NO thus formed is recycled and aqueous HNO3 can be concentrated. सो इस मेथड से जो कॉन्सेंट्रेशन बनती है HNO3 की, वो 68% बाय मास होती है. फर्दर अगर हमें वो 98% की कॉन्सेंट्रेशन पे लाना है HNO3 को, तो हम उसको डिहाइड्रेट करते हैं H2SO4 से. So H2SO4 is also a good dehydrating agent. ठीक है. So 68 Ostwald प्रोसेस से हमें 68% मिलता है HNO3 और उसको फर्दर डिहाइड्रेट कर देंगे तो वो 98% की कॉन्सेंट्रेशन पे मिल जाएगा. ठीक है. So HNO3 is a colorless liquid and it is a very strong acid. So in water, HNO3 completely dissociates in water to give NO3 minus and H3O plus. So ये प्रोटॉन देता है वाटर में. So it's a very strong acid and NO3 minus is also a very strong oxidizing agent. We'll just see. So it is a colorless liquid. In the lab, what we use contains 68% of HNO3 by mass. If you talk about its structure, it is a planar structure. ठीक है. ये वाले जो दो बॉन्ड्स हैं ऑक्सीजन के साथ, यहाँ पे देयर इज अ पॉसिबिलिटी ऑफ अ पाई बॉन्ड. सो इसका स्ट्रक्चर ऐसे बनाते हैं. और ये अदरवाइज ऐसे. ठीक है. सो यहाँ पे कि जो पाई बॉन्ड है ये इधर रेजोनेंस में है. सो ये बॉन्ड लेंथ 121 है और ये वाला सिंगल बॉन्ड है ऑक्सीजन के साथ. सो दिस इज अ लॉन्गर बॉन्ड. ये 140.6 है और ये वाला HNO3 में दिस बॉन्ड इज शॉर्टर बिकॉज देयर इज अ डबल बॉन्ड कैरेक्टर हियर. ओके. सो इन द गैसियस स्टेट इट एग्जिस्ट एज अ प्लेनर मॉलिक्यूल. In aqueous solution, nitric acid behaves as a strong acid. We just discussed this here. So we get NO3 minus ions. Concentrated nitric acid is a very strong oxidizing agent and it attacks most metals except gold and platinum. So सारे metals, most of the metals HNO3 में dissolve हो जाते हैं except gold and platinum. Gold और platinum noble metals हैं. Au and platinum. So ये HNO3 में नहीं होते because they least reactive of the metals हैं. What do they dissolve in? They dissolve in aqua regia. So what is aqua regia? It is a 75% mixture of HCl, concentrated HCl, which is 75% plus 25% of concentrated HNO3. So इस मिक्सचर के अंदर विच इज कॉल्ड एक्वा रिजिया, even gold and platinum dissolve. So what is it about aqua regia जो HNO3 में तो नहीं dissolve हो रहे, but if we have a mixture like this, gold and platinum also dissolve, because one, the contributing factors are the high oxidizing nature of NO3 minus ions, and secondly the ability of Cl minus ions from HCl, the ability of Cl minus ions, chloride ions to form complexes with metals. So इन दोनों की जब ये abilities को combine कर देते हैं तो ये जो mixture है it can even dissolve noble metals like gold and platinum. So let's see how nitrogen, how HNO3 reacts with metals. So apart from gold and platinum, rest of the metals. So the ability of HNO3 depends on its concentration. So वो किस तरीके से रिएक्ट कर रहा है, क्या प्रोडक्ट फॉर्म हो रहा है, वो उसकी कॉन्सेंट्रेशन पे डिपेंड करता है. वो डाइल्यूट है कि कॉन्सेंट्रेशन कॉन्सेंट्रेटेड है. It depends on the temperature conditions and it also depends on the type of metal that we are using. So in all the cases HNO3 oxidizing agent है तो वो खुद reduce हो जाता है. So either it forms NO or it forms NO2 or it forms N2O. ठीक है, reduce सब में हो रहा है. अगर हम copper की बात करें with dilute HNO3, these reactions are very important. So copper with dilute HNO3 gives us copper nitrate and NO. So HNO3 में ये +5 स्टेट में है, NO में ये +2 स्टेट में आ गया. ठीक है, copper with concentrated HNO3 gives us copper nitrate and NO2. NO2 में it is in the +4 state. ठीक है, if we talk about zinc, zinc on reaction with dilute HNO3 gives zinc nitrate. corresponding nitrate salt तो बन ही रहा है. HNO3 किस चीज़ में रिड्यूस हो रहा है, इधर N2O, नाइट्रस एसिड N2O. सो इधर इसका ऑक्सीडेशन स्टेट क्या है, +1. एंड if it's reacting with concentrated HNO3, we are getting zinc nitrate and NO2, where the state is +4. So in all these cases, these metals are dissolving in HNO3 and we are getting different products depending on the concentration of HNO3. तो यहाँ पे dilute के साथ NO बन रहा है, concentrated के साथ NO2. Here in the case of zinc, with dilute we get N2O and with concentrated we get NO2. Now some metals like chromium or aluminium do not dissolve. So हमने ये aluminium के केस में डिस्कस किया था. Aluminium can be transported, HNO3 can be transported in aluminium containers. It's the same thing here. So when HNO3 is put in an aluminium container, what happens? A thin layer of aluminium oxide is formed because HNO3 is an oxidizing agent also. So because of that layer, the rest of the metal becomes passive or it is stopped from reacting with HNO3. तो वो safely carry कर सकते हैं. Similarly is the case with chromium. So chromium or aluminium concentrated nitric acid may form a passive film of oxide on the surface. This was the reaction of HNO3 with metals. Now HNO3, concentrated HNO3 also reacts with non-metals. Non-metals के साथ react करके it oxidizes the non-metal and itself gets reduced. So हर केस में concentrated HNO3 there also NO2 में reduce हो रहा था and in the case of non-metals also वो NO2 में ही reduce हो रहा है. So with iodine we get iodic acid, with carbon we get carbon dioxide, with S8 that is sulfur we get H2SO4, and with P4 that is white phosphorus we get H3PO4 or phosphoric acid. So these are the reactions of HNO3 with metals and non-metals, and HNO3 is an oxidizing agent. अब there is a slight confusion कि HNO3 की oxidation state +5 है और नाइट्रोजन की वैलेंसी कोवैलेंसी cannot exceed 4. So दोनों में difference क्या होता है? If we go back to the structure, covalency is the number of electron pairs shared. So नाइट्रोजन कितने electron pairs share कर रहे हैं यहाँ पे? 1, 2, 3 and 4. So covalency 4 हो गई. बिकॉज और नाइट्रोजन के पास वैलेंस इलेक्ट्रॉन्स कितने हैं टोटल 5. सो जो ऑक्सीडेशन स्टेट है वो है कितने वैलेंस इलेक्ट्रॉन्स को वो यूज़ कर रहा है इन फॉर्मिंग द कंपाउंड. सो वैलेंस इलेक्ट्रॉन्स 5 के 5 यूज़ हो रहे हैं, दैट्स वाई ऑक्सीडेशन स्टेट HNO3 की +5 है. और क्योंकि the number of electron pairs that are being shared or the number of bonds that are getting formed are 4, तो उसकी covalency 4 है. ठीक है. Alright, so the last topic in under HNO3 is the brown ring test. Brown ring test is a test used for detection of nitrates. So if we have a compound given to us in salt analysis and it's an unknown compound, सो जब आप उसके सब्सिक्वेंट टेस्ट करते हो उनमें से एक टेस्ट करते हो द टेस्ट फॉर नाइट्रेट आयंस, उसका एनायन पता करने के लिए. NO3 माइनस के लिए. सो इस टेस्ट में क्या करते हैं, इफ वी हैव एन एक्वस सॉल्यूशन ऑफ द गिवन नाइट्रेट, उसके अंदर हम डाइल्यूट FeSO4 फेरस सल्फेट सोल्यूशन डालते हैं, एक्वस डाइल्यूट फेरस सल्फेट. सो यहाँ पे हमारा नाइट्रेट का सोल्यूशन है टेस्ट ट्यूब में और हमारा फेरस सल्फेट का सोल्यूशन है. अब हम एक ड्रॉपर में कॉन्सेंट्रेटेड H2SO4 लेके ड्रॉप वाइज साइड से डालते हैं और यहाँ पे H2SO4 की लेयर हो जाती है. नाउ एट द जंक्शन जहाँ पे H2SO4 और एक्वस लेयर टच कर रही है वहाँ पे एक brown colored ring form होती है, which tells us if that ring is getting formed, it tells us that हमारे given solution में nitrate ions थे. अब ये किस चीज़ पे डिपेंड करता है? Firstly, this depends on the ability of the Fe2 plus ions to reduce HNO3 to NO. We'll see how. दूसरा, it depends on the ability of NO nitric oxide to form complexes with metal ion. So what happens first, जब हम इसमें H2SO4 डालते हैं, in the first step NaNO3 reacts with H2SO4 और हमारे को क्या मिलता है, if you go back to the reaction of preparation, this one NaNO3 plus H2SO4 gives us sodium hydrogen sulfate and HNO3. सो फर्स्ट स्टेप में हमारा HNO3 फॉर्म होता है. ठीक है, प्लस सोडियम हाइड्रोजन सल्फेट. अब सेकेंड स्टेप में लुक एट दिस रिएक्शन हियर. सो जो हमारा NO3 माइनस है फ्रॉम HNO3 देयर, दिस इज फ्रॉम HNO3. Fe2 प्लस इज फ्रॉम द एक्वस सोल्यूशन ऑफ फेरस सल्फेट जो हमने ऐड किया हुआ था, और H प्लस इज फ्रॉम H2SO4. ये तीनों मिला के क्या करते हैं, Fe2 प्लस गेट्स ऑक्सीडाइज टू Fe3 प्लस एंड इट रिड्यूसेस NO3 माइनस टू NO. और NO3 माइनस इज अ स्ट्रॉन्ग ऑक्सीडाइजिंग एजेंट, तो वो सेल्फ वो रिड्यूस हो जाता है और इसको ऑक्सीडाइज कर देता है. अब ये जो NO फॉर्म हुआ है, जो रिमेनिंग हाइड्रेटेड, क्योंकि एक्वस सॉल्यूशन था, हाइड्रेटेड Fe2 प्लस जो आयंस थे उसके साथ NO एक कॉम्प्लेक्स फॉर्म करता है विच इज FeH2O5NO. सो हाइड्रेटेड आयन में 6 वाटर मॉलिक्यूल्स थे. जो ब्राउन रिंग बनती है विच इज अ कॉम्प्लेक्स विद NO, उसमें 5 वाटर मॉलिक्यूल्स एंड NO है और टोटल कॉम्प्लेक्स पे चार्ज है 2 प्लस. दिस गिव्स द ब्राउन रिंग विच इज द टेस्ट फॉर नाइट्रेट्स. सो यू अंडरस्टूड इसमें क्या क्या होता है. पहले स्टेप में H2SO4 रिएक्ट्स विद द सोर्स ऑफ नाइट्रेट. यहाँ पे मैंने उसको सोडियम नाइट्रेट लिखा है. सो कोई भी आपका सॉल्ट गिवन है जिसमें नाइट्रेट हो, सो दैट रिएक्ट्स विद H2SO4 गिविंग अस HNO3. उसके बाद HNO3 reacts with FeSO4 and in the presence of an acidic medium which is H2SO4 to give us NO. जब NO फॉर्म हो जाता है, NO reacts with the hydrated Fe2 plus ions to give us the brown ring, and this is the brown ring test. So this concludes nitric acid. अब नाइट्रोजन के सारे कंपाउंड्स खत्म हो गए. Now we will move on to phosphorus. Okay, so phosphorus is present in many allotropic forms. उसकी 3 मेन एलोट्रोपिक फॉर्म्स जो हमें पढ़ने हैं वो है वाइट फॉस्फोरस, रेड फॉस्फोरस एंड ब्लैक फॉस्फोरस. So if we talk about white phosphorus, obviously it is white colored, it's a waxy solid. Now it is insoluble in water, but it is soluble in carbon disulfide. Another important property is that it reacts with moist air and gives off light, or you can also say it glows in the dark. So this property where it glows in the dark is called chemiluminescence. So this is a property only given by white phosphorus and not the rest of the allotropes of phosphorus. So it is insoluble in water, it is poisonous, and it is soluble in carbon disulfide CS2, and it glows in the dark, which is called chemiluminescence. Now, a very interesting property of white phosphorus is that it spontaneously catches fire in air. So white phosphorus reacts with oxygen in the air to give P4O10. It spontaneously catches fire in air. Now, because of this, it is stored under water. To prevent the reaction, because water से वो react नहीं करता, air में वो spontaneously fire catch कर लेते और P4O10 बन जाता है, that is the oxide of phosphorus. अब ये spontaneously air में क्यों react करता है? Why is it so reactive? ये इतना ज़्यादा reactive इसलिए है because it has an angular strain. For that we have to talk about the structure of white phosphorus. So the structure is this. It is a tetrahedral structure and the bond angle P bond angle is 60 degree. So there is a large angular strain because the angle is very small. So इसमें हर phosphorus 3 और phosphorus से attached है, 1, 2, 3. ये phosphorus भी 3 से attached है, 1, 2, 3. और ये phosphorus भी, सारे phosphorus के 3 bonds हैं. All right. So ये जो tetrahedral structure है, it's P4 molecule. So white phosphorus is P4. Discrete molecules होते हैं P4 के. ठीक है. अब इसमें जो angle है phosphorus के बीच में वो 60 डिग्री है, which is a very small angle. सारे compounds में जो भी हम angle की बात करते हैं तो हमेशा ये बात होती है कि वो least ऑब्जेक्शनल एंगल अज्यूम करते हैं, मतलब मोस्ट स्टेबिलिटी वाला एंगल अज्यूम करते हैं. तो टेट्राहेड्रल स्ट्रक्चर भी इसलिए फॉर्म होता है क्योंकि 109.28 का एंगल सबसे ज़्यादा स्टेबल है अगर 4 बॉन्ड्स हैं. अब यहाँ पे जो पी का एंगल है वो 60 डिग्री, इट्स अ वेरी स्मॉल एंगल, तो बहुत ज़्यादा एंगुलर स्ट्रेन है मॉलिक्यूल में. सो इट्स वेरी रिएक्टिव, इट्स रेडी टू रिएक्ट विद वॉट एवर इट कैन फाइंड. सो ये ऑक्सीजन के साथ बहुत जल्दी रिएक्ट करता है, P4O10 बना के रखता है. तो दैट इज द रीजन वाई इट इज स्टोर्ड अंडर वाटर. Now if you talk about red phosphorus is obtained when you heat white phosphorus at 300 degrees Celsius in an inert atmosphere for several days. ठीक है. White phosphorus को several days के लिए जब heat करते हैं तो वो red phosphorus बनता है which has an iron grey luster. अब red phosphorus और white phosphorus में difference क्या है structure में? सो रेड फॉस्फोरस में सारे P एक दूसरे से अटैच्ड है. रेड फॉस्फोरस इज पॉलीमेरिक. सो इसमें ये है, ये दोनों फॉस्फोरस आपस में बॉन्ड नहीं बनाते, ये इधर दूसरे फॉस्फोरस से बॉन्ड बना रहे हैं. सो टेट्राहेड्रल मॉलिक्यूल की चेन है. अब इधर ठीक है, इधर फिर से P एंड सो ऑन. सो इट्स अ पॉलीमेरिक चेन ऑफ P4. तो मोनोमर इसका P4 है. इट फॉर्म्स अ पॉलीमेरिक चेन अपॉन हीटिंग फॉर सेवरल डेज. सो उससे बन जाता है रेड फॉस्फोरस. नाउ रेड फॉस्फोरस इज मच मोर स्टेबल. सो रेड फॉस्फोरस डज नॉट कैच फायर इन एयर स्पॉन्टेनियसली, जैसे ये वाला रिएक्शन रेड फॉस्फोरस के साथ नहीं होता. सो रेड फॉस्फोरस डज नॉट हैव टू बी स्टोर्ड अंडर वाटर. नाउ रेड फॉस्फोरस इज इनसॉल्युबल in water as well as CS2. whereas white phosphorus water में तो insoluble था, CS2 में soluble था. Okay, red phosphorus is also odorless and non-poisonous. White phosphorus poisonous है, ठीक है. It is much less reactive than white phosphorus and it does not glow in the dark. So these are the differences between white and red phosphorus जो कभी कभी एग्जाम में आ जाते हैं. So chem illuminescence ये नहीं शो करता red phosphorus, जबकि white phosphorus ये शो करता है. The last is black phosphorus, the allotrope of phosphorus that you have to study. So black phosphorus के two forms होते हैं, alpha black और एक beta black. So alpha black red phosphorus से बनता है. When it is heated in a sealed tube at 803 Kelvin, it has an opaque monoclinic or rhombohedral crystal structure and it does not oxidize in air. तो ये भी उतनी easily oxidize नहीं होता. और beta black phosphorus is prepared by heating white phosphorus. तो ये alpha red से बनता है और beta white से बनता है. Under high pressure उसको 473 Kelvin पे heat करने से. Beta B does not burn in air up to 673 Kelvin. So red phosphorus भी up to 400 degree Celsius air से react नहीं करता, because उसमें वो angular strain को हमने थोड़ा सा reduce कर दिया, right? वो polymeric chain बन गई. So वो जो 60 degree का angle था वो पूरे में नहीं है, पूरे जो P4 unit है. So that's why red phosphorus भी 400 degrees तक react नहीं करता air से. And this is black phosphorus, alpha and beta. दोनों ही उतने ज़्यादा reactive नहीं है, oxidize नहीं होते. और ये red से बनता है, वो white से बनता है, ठीक है. So these are the allotropes of phosphorus. Next important compound of phosphorus is the hydride of phosphorus, which is called phosphine. Phosphine is PH3. Now phosphine has a very bad smell. So a garlicky, bad fish smell, and it is highly poisonous. It is toxic. Phosphine is toxic because it forms a complex with hemoglobin. जैसे हमने कार्बन मोनोऑक्साइड के लिए पढ़ा था, बिल्कुल वैसे. So phosphine forms a complex with hemoglobin and it starves the body of oxygen. That's why it is toxic. If you talk about the preparation of phosphine, the first method is using metal phosphides. So अगर हम calcium phosphide का reaction करें with water or calcium phosphide with an acid like HCl. So calcium phosphide Ca3P2, valency of calcium is 2, phosphorus is 3, so Ca3P2 on reaction with water gives us calcium hydroxide and PH3. It's a gas. Similarly, calcium phosphide with HCl also gives calcium chloride and phosphine. So now an inert atmosphere of CO2 is required. Why is this inert atmosphere of CO2 required here? In this next reaction, where white phosphorus is boiled with NaOH. So this is white phosphorus. On boiling with NaOH also gives us phosphine. An inert atmosphere of CO2 is required here. Can you think why? So अगर ऑक्सीजन में हमने white phosphorus को NaOH के साथ boil कर दिया, what will happen? White phosphorus react कर जाएगा ऑक्सीजन के साथ and P4O10 आ जाएगा. We do not want that. We don't want an oxide. What do we want? We want phosphine. So इसलिए हम inert atmosphere लेते हैं. So this is the second reaction. So white phosphorus on boiling with NaOH gives us phosphine and sodium hypophosphite, NH2PO2. ठीक है? This is the second reaction. Now phosphine is basic in nature. ये हमें किस reaction से पता चलता है? So phosphine reacts with HBr to give us PH4Br, or you can say it reacts with HI to give us PH4I. So in both these cases, what is phosphine doing that it is reacting with acids like HBr and HI? Phosphine has a lone pair जो वो इस पे donate करके ये वाला compound form कर रहा है. So these reactions tell us that phosphine is a Lewis base. अब phosphine को इसमें कभी कभी impurities present होती हैं, बहुत ही interesting reaction है. So बेसिकली फॉस्फीन में समटाइम्स डाइफॉस्फीन भी होता है, सो P2H6, और समटाइम्स फॉस्फीन में P4 भी होता है, वाइट फॉस्फोरस। अब ये दोनों जो है, फॉस्फीन डज नॉट स्पॉन्टेनियसली रिएक्ट विद एयर, वो एयर में एकदम से फायर नहीं कैच करता, बट उसमें अगर P2H6 और P4 की इम्प्योरिटी है, ये दोनों जो कंपाउंड्स हैं ये एयर में एकदम से फायर कैच कर लेते हैं। सो दिस, बिकॉज ऑफ दिस पर्टिकुलर रिएक्शन, मार्शी एरियाज में फ्लिकरिंग लाइट्स दिखती हैं, जिनको बोलते हैं विल ओ द विस्प। सो जो फ्लिकरिंग लाइट्स मार्शी एरियाज में दिखती हैं, दैट इज बिकॉज ऑफ द रिएक्शन ऑफ दीज इम्प्योरिटीज प्रेजेंट इन फॉस्फीन, जो एयर में स्पॉन्टेनियसली फायर कैच कर लेती हैं। सो ये एक फिनोमिना है जो पैरानॉर्मल से लगता है इफ़ यू सी इट फ्रॉम अ डिस्टेंस, कि सडनली वहाँ पे लाइट दिख रही है, बट दैट इज बिकॉज ऑफ दिस पर्टिकुलर रिएक्शन विद oxygen from the air. So that's called will o the wisp. Now, to purify whatever phosphine we have from impurities, first it is absorbed in HI. So HI में वो क्या रिएक्शन देता है? It forms phosphonium iodide PH4I, because वो basic है nature में. अब PH4I when treated with KOH, this reaction here, it gives us pure phosphine. So PH4I with KOH or NaOH gives us KiH2O and phosphine. So purification of phosphine is a two-step process. In the first step we take into account the basic nature. So वो react करता है HI के साथ to form PH4I. PH4I when absorbed on KOH or NaOH gives us phosphine. This is the method of purification of phosphine. Okay, now coming to the properties, it is a colorless gas, rotten fish smell and highly poisonous. It explodes in contact with traces of oxidizing agents like HNO3, Cl2 and Br2 vapors. So इनके साथ ही explode कर जाता है. It is slightly soluble in water. A solution of pH3 in water decomposes in the presence of light, गिविंग रेड फॉस्फोरस एंड H2. ये थोड़ा सा डिफरेंस है अमोनिया के वाटर रिएक्शन में और फॉस्फीन के. सो फॉस्फीन का सोल्यूशन वाटर के साथ डिकम्पोज कर जाता है टू फॉर्म रेड फॉस्फोरस एंड हाइड्रोजन गैस. ठीक है. नाउ बिकॉज व्हेन अब्सॉर्ब्ड इन कॉपर सल्फेट और मर्क्यूरिक क्लोराइड सोल्यूशन, फॉस्फीन क्या करता है, फॉस्फाइड्स बन जाते हैं. तो कॉपर सल्फेट के साथ इफ फॉस्फीन इज रिएक्टिंग, सो विल गेट कॉपर फॉस्फाइड एंड H2SO4. सिमिलरली HgCl2 के साथ इफ फॉस्फीन रिएक्ट्स, वी गेट Hg3P2 and HCl. So this is a reaction of phosphine with metal sulfates or chlorides. Now it is weakly basic, we have already discussed, because it gives this reaction with an acid like HBr or HI. Already done. Now another interesting thing is the bond angle in phosphine. So we have already discussed what is the bond angle in phosphine जब हमने hydrides किए थे. But if you compare phosphine with phosphonium ion PH4 plus, you will find that the bond angle in PH4 plus is higher. Why is that happening? So if we draw the structure, और इसके अंदर PH4 plus, one of the positions in phosphine is occupied by a lone pair. इस lone pair से, because of the repulsions between the lone pair and the bond pair, these angles contract and they become small. Whereas यहाँ पे lone pair की जगह एक bond pair है PH. So bond pair repulsions are less than lone pair bond pair, because lone pair ज़्यादा space occupy करते हैं around the central atom, तो repulsion भी ज़्यादा होती है. So because यहाँ पे lone pair की जगह एक bond pair है, so repulsion कम है, तो इसलिए ये bond angle is large compared to the one in phosphine. That is the reason that bond angle in PH4 plus is higher than in phosphine. Okay, the last two important topics for halides of phosphorus are PCl3 and PCl5. So phosphorus forms two types of halides, trihalides and pentahalides. Here you will remember the difference between nitrogen. So nitrogen does not form pentahalides. Okay, nitrogen only forms trihalides. Phosphorus forms both types of halides. Now let us see their properties separately. So if you talk about phosphorus trichloride, that is PCl3. In PCl3, phosphorus is sp3 hybridized. So it has a tetrahedral geometry. And there is a lone pair. Okay. So tetrahedral geometry. And sp3 hybridization, so pyramidal shape. Now how do you prepare PCl3? One is by passing dry chlorine over heated white phosphorus. So P4 plus 6Cl2. This 6 is very important because जब हम PCl5 देखेंगे then we'll see 6 molecules of Cl2 के साथ ये PCl3 दे रहे हैं, but if we have excess of chlorine gas तो वो PCl5 देता है. So white phosphorus with Cl2 gives PCl3. Now PCl3, अच्छा so ये ड्राई क्यों है? यहाँ पे क्वेश्चन आता है कि यहाँ पे हम ड्राई क्लोरीन क्यों नहीं यूज़ कर रहे, हम एक्वा सोल्यूशन क्यों नहीं यूज़ कर सकते. ड्राई वर्ड स्पेसिफिकली इसलिए मैंशनड है बिकॉज जो PCl3 फॉर्म होता है वो वाटर में P4 तो नहीं रिएक्ट करता वाटर के साथ. ओके, P4 इज नॉट सॉल्युबल इन वाटर बट PCl3 वाटर में हाइड्रोलाइज हो जाता है. सो टू प्रिवेंट दैट, जस्ट बिकॉज वी नीड PCl3 एज द प्रोडक्ट, हम ड्राई गैस यूज़ करते हैं यहाँ पे. ठीक है. The second reaction of PCl3 preparation is the action of thionyl chloride on white phosphorus. So SOCl2 is thionyl chloride. So thionyl chloride on white phosphorus gives PCl3, SO2 and S2Cl2. S2Cl2 क्या है? मोनोहेलाइड है सल्फर का. ये हम चाल्कोजेन फैमिली, द ऑक्सीजन फैमिली में पढ़ेंगे. सो सल्फर का जो मोनोहेलाइड बनता है SCl, सारे मोनोहेलाइड्स आर ऑलवेज प्रेजेंट एज डाइमर्स. तो ये S2Cl2 इज द मोनोहेलाइड ऑफ सल्फर विच इज प्रेजेंट एज अ डाइमर. सो ऑन रिएक्शन ऑफ व्हाइट फॉस्फोरस विद thionyl chloride SOCl2 we get PCl3. Coming to the properties, it is a colorless oily liquid. जो PCl5 है वो येलो वाइट पाउडर होता है. This is a liquid, colorless oily liquid. Now just like we spoke about, it hydrolyzes in the presence of moisture. So what are the products of hydrolysis of PCl3? ये भी बड़ा important question है, कभी कभी आ जाता है. Products of hydrolysis of PCl3 मतलब PCl3 reacting with water gives us phosphorus acid. Phosphorus acid and HCl, H3PO3 and HCl. So hydrolysis पे PCl3 के ये products है. We'll contrast them with the products of PCl5 on hydrolysis. The next important reaction is PCl3 reacting with organic compounds. अब ये दोनों reaction हैं, ये already haloalkanes में करे हुए हैं, alcohols में करे हुए हैं, carboxylic acids में करे हुए हैं. So remember, अगर हमें substitution reaction with chlorine करना होता है तो हम PCl3 as one of the agents use करते थे. So we have acetic acid here, CH3COOH. इससे हमें CH3COCl मिल गया, plus we get orthophosphorus acid again, H3PO3. And if we have an alcohol, this was a carboxylic acid. Alcohol में भी OH को nucleophilic substitution से we can make an alkyl halide using PCl3. Okay, so PCl3 से react करके we'll get ethyl chloride and again orthophosphorus acid. These are the two reactions which we have done in organic chemistry also. Now structure of PCl3 we've already discussed. तो ये sp3 hybridized है and this is the structure. So ये pyramidal है, तीनों Cl bonds और ऊपर एक lone pair है. Now let us see PCl5 इससे different कैसे है. So phosphorus pentachloride. If you talk about the preparation, जस्ट लाइक आई सेड वाइट फॉस्फोरस का रिएक्शन विद एक्सेस ऑफ ड्राई क्लोरीन. ड्राई क्लोरीन क्यों यूज़ कर रहे हैं? बिकॉज ड्राई क्लोरीन में क्या होगा, अगर ड्राई नहीं लेंगे तो वाटर होगा और वो हाइड्रोलाइज कर जाएगा. बट हमें वो नहीं कराना और हमें PCl5 चाहिए, तो हम क्या करेंगे, वील हैव ड्राई क्लोरीन इन एक्सेस. तो वहाँ पे 6 मोल्स थे क्लोरीन के, यहाँ पे कितने हैं, 10 मोल्स ऑफ क्लोरीन. So P4 reacting with 10 moles of chlorine gives us PCl5. दूसरा रिएक्शन वहाँ पे थायोनिल क्लोराइड था, यहाँ पे क्या है, SO2Cl2. सो ये बहुत ज़्यादा कन्फ्यूजन का मैटर होता है. दिस इज नॉट थायोनिल क्लोराइड, दिस इज सल्फ्यूरिल क्लोराइड. सो इसका सेकेंड मेथड ऑफ प्रिपरेशन इज फ्रॉम सल्फ्यूरिल क्लोराइड. सो P4 with SO2Cl2 gives PCl5 and SO2. सो प्रोडक्ट्स भी डिफरेंट हैं. ओके, सो उसमें कंफ्यूज नहीं होना, वो थायोनिल क्लोराइड था, ये SO2Cl2 है. White phosphorus reacting with SO2Cl2 gives PCl5 and SO2. These are the two methods of preparation. Now coming to the properties, वो colorless oily liquid था. PCl5 is a yellowish white powder. How does it hydrolyze in air? So in moisture. So in the presence of moist air, it hydrolyzes in 2 steps. So इसका पहला step क्या है? PCl5 water के साथ in the first step gives us POCl3 and HCl. जो ये POCl3 है, this Cl. ये बड़ा इंटरेस्टिंग कंपाउंड है बिकॉज हमने पढ़ा था जो ये 5 बॉन्ड्स हो रहे हैं फॉस्फोरस के फॉर्म, ये वाला ऑक्सीजन के साथ जो पाई बॉन्ड है, दिस इज D pi P pi. This is not P pi P pi with oxygen. It is D pi P pi with oxygen. So POCl3 and HCl. In the second step, ये POCl3 further hydrolyze हो जाता है to give us phosphoric acid and HCl. So ये है phosphoric acid. Plus HCl. PCl3 के केस में phosphorus acid is one of the products and PCl5 के केस में जो फाइनल प्रोडक्ट इज phosphoric acid. दोनों एसिड्स डिफरेंट हैं. सो इन दोनों में जो डिस्टिंग्विश करने वाले फैक्टर्स हैं वो याद रखने वाली बात है. सो H3PO4 है, उस वाले केस में H3PO3 था. सो दिस इज द हाइड्रोलिसिस. नाउ व्हेन हीटेड, फर्स्ट इट सबलाइम्स, बट ऑन फर्दर हीटिंग वो डीकम्पोज हो जाता है ऑन स्ट्रॉन्गर हीटिंग टू गिव अस PCl3 एंड Cl2. अब इस रिएक्शन से क्या पता चल रहा है, इसमें इसकी स्टेट थी +5, तो ये इसमें +3 स्टेट में आ गया. सो ये रिड्यूस हो गया. नाउ इफ यू टॉक अबाउट द रिडक्शन पोटेंशियल, सो PCl5 इज अ रिड्यूसिंग एजेंट. सो इस रिएक्शन में व्हेन इट इज हीटेड विद मेटल्स, व्हाट इज हैपनिंग, PCl5 के पास पॉसिबिलिटी है कि वो +3 स्टेट में आ जाए. +5 से +3 में इट कैन फॉर्म PCl3. तो PCl5 इज एन ऑक्सीडाइजिंग एजेंट, तो वो सिल्वर को ऑक्सीडाइज कर देता है टू AgCl. सो सिल्वर की ऑक्सीडेशन स्टेट 0 से +1 हो गई और इटसेल्फ वो PCl3 बना लेता है. तो ये दोनों क्या है, रिएक्शन विद मेटल्स ऑफ PCl5 आर रिडक्शन रिएक्शंस ऑफ PCl5. दूसरा टिन के साथ भी PCl5 कैन रिएक्ट टू गिव टिन क्लोराइड एंड PCl3. तो यहाँ पे भी इसकी ऑक्सीडेशन स्टेट चेंज हो गई 0 से +4. सो इट कैन ऑक्सीडाइज मेटल्स बिकॉज इट itself कैन गेट reduced to PCl3. So it does not act as both a reducing and an oxidizing agent. It can only reduce its own oxidation state. So ये सिर्फ ऑक्सीडाइजिंग एजेंट है. Now ये भी ऑर्गेनिक कंपाउंड्स के साथ रिएक्शन करता है जस्ट लाइक PCl3. तो यहाँ पे अल्कोहल के साथ PCl5 में वी गेट इथाइल क्लोराइड. जो बाकी के प्रोडक्ट्स हैं दैट वेरी इन द केस ऑफ PCl3 एंड PCl. So POCl3 and HCl. Similarly, if we have acetic acid reacting with PCl5, we get CH3COCl, POCl3 and HCl. Now it is a solid. Solid state में ये कैसे exist करता है? It exists as an ionic compound. So that ionic compound contains PCl4 plus and PCl6 minus ions. So जो anion है PCl6 minus है, तो ये octahedral है, और जो cation है वो PCl4 plus है जो tetrahedral है. The last thing under PCl5 is its structure. So the structure of PCl5 is trigonal bipyramidal. So ट्राइंगल बाइपिरामिड में सिर्फ दो चीज़ें इंपॉर्टेंट हैं. पहली बात तो इसकी हाइब्रिडाइजेशन क्या होगी. सो ये हमारे ऑर्बिटल्स हैं 2 3 4 5 5 बैलेंस इलेक्ट्रॉन्स, 5 के 5 क्लोरीन एटम्स के साथ अटैच्ड हैं. सो ये क्या हो गई sp3d. सो इसकी हाइब्रिडाइजेशन sp3d है. दूसरा पॉइंट इंपॉर्टेंट टू रिमेंबर इज ये जो बॉन्ड लेंथ है ऑफ द एक्सियल बॉन्ड्स PCl एंड PCl हेयर, जो फॉस्फोरस के ऊपर और जो नीचे बॉन्ड है जो 90 डिग्री पे है विद द प्लेन, ये बॉन्ड लेंथ आर लॉन्गर दैन द वंस ऑन द इक्वेटोरियल प्लेन, क्योंकि एक्सियल बॉन्ड लेंथ ज़्यादा रिपल्शन सफ़र करती है. इसका छोटा सा डिटेल नेक्स्ट क्लास में कर लेंगे बिकॉज आवर टाइम इज ओवर. सो यू नीड टू रिमेंबर दैट द एक्सियल लेंथ्स आर लॉन्गर दैन द इक्वेटोरियल बॉन्ड लेंथ्स. सो दिस फिनिशेज आर हेलाइड्स ऑफ फॉस्फोरस. हमारा सिर्फ एक टॉपिक रह गया ऑक्सो एसिड्स ऑफ फॉस्फोरस, वो हम अब नेक्स्ट क्लास में करेंगे. जो हमारी ग्रुप 16 की क्लास है उसमें हम ऑक्सो एसिड्स फिनिश करेंगे और हम फिर सैटरडे को मिलेंगे इसके बाद टू स्टार्ट ग्रुप 16 द चैल्कोजेंस. ऑलराइट, थैंक यू सो मच फॉर वॉचिंग. आई विल सी यू. अभी 15 मिनट्स के बाद सिलेक्शन आवर स्टार्ट हो रहा है, सो उसमें हम ग्रुप 15 के ही सारे टॉपिक्स करेंगे. आई विल सी यू. थैंक यू.